Swayam Prabha. Digital India. Educated India.
So let's start then. So there are a good mix of MS and PhD, mostly PhD, and those of you are in MS who hopefully will get motivated to continue to do your PhD. Okay, let's think that's going to happen. All right, so I've already showed you this example. Okay, I only need to say one thing here, is that you see this line here which I didn't show before. So basically these lines are called constraint lines or constraints. There could be one or there could be more than one. At any point of time you can interrupt and ask questions. Okay. So what the constraint do is that it doesn't make the entire XY space that you see, we call it design space also, or variable space, feasible. So this constraint says anything that is inside this ellipse is feasible. That means outside this it violates some basic principle, maybe some physics, maybe they will foul with each other if you make one thing too big. So this is not allowed. So if I take a point here, I can compute the function value, the cost, but it's of no interest to me because I cannot manufacture it. It's going to fail. So but anything I do here is not going to fail because it satisfies the constraints or a set of constraints. So if you have multiple constraints, the common area that satisfies all the constraints is called the feasible space. So now with this, the optimization task can be defined as a task of searching for a set of design variables or decision variables which would minimize or maximize one or more objective function. We talked about single and multiple, right? And that solution is also, or solution set is also going to satisfy all the constraints. So these three things I put in red color are the thing as a applicationist you need to figure out. For your problem, what are the design variables? Are there two, are there one, are there 100, or are there a million of them? So you need to decide on that. Then you need to decide what are my performance measures. Once I have a set of design variables, I can visualize a design or I can go and implement the design, but what is that I'm looking for, what I'm trying to minimize or maximize. So you need to decide on the objective functions, and then you need to check, in fact before you do the objective function you need to check if my solution is feasible, does it satisfy all my constraints. So all the thing you studied in your undergrads, let's say in a particular area, fluid mechanics for example, so you studied all these equations starting with Navier-Stokes and lots of thumb rule principles that fluid mechanics have, those needs to be satisfied. Okay, otherwise it's not a feasible design. So when I do that, then I say it's feasible, and then I'm interested in saying how much would it cost, how much would be the friction or anything, how much would be lift or drag, whatever you want to do, right? Okay, so again design variables xy, objective function f in the case of this example, and constraint function can be both equality or inequality, which I'm going to talk to you about later. Okay, so in this particular case this is an inequality constraint, and you can see that these are sometimes called the contour functions of the objective function. So I may not need to show you this. If I can plot the contour, I can only do it for two variables, right? And it says that the function value reduces as you come in any direction, and eventually this becomes the minima. So that's your goal of the optimization algorithm, to find that point. Now where do we need these methods? Here there are a few I'm showing you. First is of course the modeling. Okay, you can start from either end, but these two are the most important ones where optimization is used. Modeling is, you have a complex engineering system in your area, manufacturing process for example, you have a CNC machine and you want to do a job with it, and you want to model that if I give so much feed, so much depth of cut, so much some other things, how good will be the quality of my finished product, right? So I want to model that because I may not have right mathematical functions. This is a blast furnace taken from materials or metallurgy. So you put in a lot of inputs into it, and it takes about 4 or 5 years of processing, and then eventually you get steel out of it. Okay, and I do not know exactly what goes on here inside. but I have lots of data. I have little bit of theory. Actually, they do a lot of theory zone wise. They put different zones, and every zone has some chemical equations happening, and then you kind of bind all of them together. All these inputs are inputs to the system. You can consider it like a system. So inputs coming in, system have a lot of subsystems, and eventually you have one or more output. Your goal is to get the good output over here, maybe the highest strength steel, the maximum strength steel. You want to know, what shall I put here? So before I do that, you need to know, you need to model these over here. So this model, if you have math equations, you have complete understanding, fine. But if you have any experience with engineering system, you know that even this steel has been produced, I think, more than 100 years now, 1905 or something when it's first started. Even now, there is not a very clear, exact understanding of what goes on. So what do you do in these cases? We haven't stopped producing steel, and we produce steel. We still make bridges with them, buildings with them, warehouses with them, and they're still standing. So not everything has to be completely understood. That's what the engineers are for. That's the difference between a scientist and an engineer. A scientist will never be happy with this. If you go and tell them to a scientist, hey, we don't have a clear idea of how steel is made, maybe that person will never cross a bridge made out of steel. Okay, it's not comfortable zone for them. But for engineers, we feel very good as long as we have verified in our labs all the boundary conditions and everything, saying if you are producing this under these boundary conditions, we have seen again and again, we've tested in our labs that this work, and on the basis of that we produce things, we continue with this. So if you want to have an understanding there, how else can I do if I don't have exact science? All you can do is, if the system has been going on for quite some time, early on it's a difficult thing, then you have to do some piloting in the lab or something and produce a lot of data. But you go to steel plant, they have, as I said, 100 years of data. Okay, they have given this input and found this steel output. They've given next day this input, another output. If they're recording, you can get lots of data. So with those data, today's machine learning or even some old way of doing modeling and predictions, you could apply to the data, optimize your model. So that modeling optimization is a big thing, which means model has some parameters, and you want to find the best parameter setting that's going to fit the data. Then there's design and manufacturing, where you can see lots of parameters, right? The angles, the thicknesses, the materials, and everything. As I said, there could be easily 400 to 500 parameters there. All these, if you give me a value for each, I can manufacture it. Okay, so then what value shall I use so that it's a lightest weight design? The weight of the whole car is the smallest, or it's the most safe design. If I have a head-on collision to the passenger here, the steering wheel in all is not going to come and penetrate. Okay, so the limited displacement that will have. So you need to have bars and struts and the stiffnesses of those, so that this part doesn't break or doesn't elongate or doesn't advance so much. So anytime you want to buy a car, go and ask what's the safety feature. And when I was buying my first car, I was curious about this, so I went and asked. I went to a Maruti showroom at that time, and I asked them, what's your safety feature? And that person was very angry at me. He thought I was checking, I was kind of demeaning the car, but I said, no, this is for my own safety, I need to know. Then he figured out and he said, this end of this is little weak. They deliberately didn't make it very strong, the joint over there. So anytime you have a collision, all the energy gets loosened from there. It just breaks that part, and all. So if it's a very rigid body, everything will move, right? But if you have a weak point, the energy vanishes from there. So that's one way to have safety, but that's not the smartest way to have, because you lost your car. If that part breaks, means you have to either throw this whole cab or repair it with a lot of repair costs. Today's car doesn't have these things. These I'm talking about maybe late 90s, middle of 90s. But these days there are a lot of other such pressure releasing or stress releasing mechanisms that they have inside the door, over there, and many other places. So it's good for you to know. So if that is what you want to do, then that's your objective function. Okay, that how much displacement your body is going to face when there is a head-on collision, when there is a side-on collision, and things like that. So any objective function you come up with, you can design a car for that. Now, obviously, in this case, you need to have multiple criteria. You don't want to have just head-on collision. A car is excellent for that. If you have little bit of a side collision, you are gone. So that's not a car you want, right? You want, for multiple criteria, you want a car to be designed. That's why multi-criteria is so important, and we're going to spend quite a bit of time. So these two, you see, will be the major applications of optimization. Then comes this scientific experiments where you do these experiments are costly, time consuming. Let's say you've already done 10 of them and you spend like 6 months doing it, and you have 2 or 3 more you could do. And we've done some such projects with the auto industries close to me in Detroit. It's very, very expensive to do one experiment. And you've already done few. The next few that you want to do, you don't want to randomly do it. You want to get maximum information out from what you've already done, make a model, and optimize and find out where you should do the next set of experiments. Okay, so that's called design of experiments area. Optimization is used there a lot. Topology optimization is another area where you want to make it lightweight or some other functionality, as I said, but now with the topology, you come up with what topology is going to minimize that. So optimization is used there, different kind of methods, but used there. Supply chain optimization. After COVID, it's become a very important thing. You need to have various suppliers sending things at the right place, the right time, so that the whole process is smooth and your production is on time and to the tune of the orders that you are looking for. Placement optimization is another thing. So here you have a little small board and you have to put a lot of things in there. Some of them are connected to each other. So in order to minimize the overall wear length, maybe you want to put those that are close by. Okay, but if you do, let's say all these are connected each other, so you want to put them close by, but then because of switching on and off between them, this part will get heated very easily, and so they call in the electronics design called hotspots, and you don't want to do that because then these equipment, these little elements there is going to get bad pretty soon. So you want to spread them. So you see the multi-criteria optimization we are talking about here. One way you want to minimize the wear length. The other case you want to minimize the effect of hotspots. They are in conflict. Always you have in conflict cost versus quality, cost versus comfort. As I mentioned, there is always this trade-off. Then control problems. Optimal control is another thing where you now don't have some design variables, but you have a design profile. Like for example, it could be a time varying thing that you have to do, or it could be a distance varying thing you have to do across a furnace. You want to maintain a certain temperature distribution inside the furnace. What is that distribution? So that you require minimal amount of fuel. You can come in the front here. So these are a bit more difficult to do, but it all comes under the optimization literature. Prediction is something where you have done maybe last 6 months worth of market data and you have modeled. With that, you can predict what's going to be in the next month or next week. If you can do that well, you can actually make a lot of money, right? As maybe some of you already do. A lot of companies are doing that. And what they do is it's modeling and then projection, right? So modeling, if you do properly, you could actually do a prediction properly as well. Then comes the data mining area where data comes from various sources. And you have to figure out this data from this source. Is it equivalent or put in the same class as that data from another source? So putting them in the same beans, okay, is called clustering. Then there are classification, and there are so many other things that are there. So every machine learning topic has a goal, has a purpose. If you look inside each of these algorithms, methods, there is an optimization task. Without that, the final result of machine learning doesn't come. So optimization is an integral part of machine learning methodology design. Then of course the final thing is any intelligent system, if you want to design like a robot, right, something autonomous, anything you want to do, if you choose your objective functions and constraints properly, this can come up with some intelligence. It can evolve intelligence, but you need to decide and design on what are these objectives that you need. It's basically what you want the robot to be. Does it look more like human? Does it like more do intelligent tasks? So what are these tasks? Once you come up with some objectives from them and make an optimization, you will observe that that design is behaving like an intelligent system. So I show this Asimov, which is the Honda's robot. It was designed way back, I think around late 2000, about 2006 or 8 or somewhere around that time. I had a collaborator from Honda, Tatsuya Okabe. So we used to work together, and he visited me while I was in Kanpur and all that. And then suddenly, for a year or two, I think about 2 years, he wouldn't reply any of my emails. And I tried to contact, I was at some point worried whether he's still alive. Then I tried to contact a lot of common friends, and all of them had the same issue, that they couldn't contact him. So we gave up. And then while I was in Kanpur, one day I was looking at the news and I see him on the news with this robot. He's standing behind them like this. And then I sent him an email that, hey, I just saw you on a Indian television here. And he said, yeah, I'm sorry for not responding for so long, because his company said you cannot even contact your family members. Once in a while you can go to them, but you cannot tell them what you're doing. So that's secretive. He was a part of this whole team that developed it. So I then asked him, why? What's his so secrecy about it? He said he didn't, because there are a lot of competition in companies, as you know. He was not allowed to say even what method they were using, and they were using evolutionary computation, which is something I'm going to talk to you about in designing all of these tasks. He was the head of the team, okay, and he was an evolutionary computing guy. So I just put this up to say that if you want, you can design intelligent systems through these optimization methods. So after this slide, if you are the dean of engineering or some head of a discipline, you come and say, hey, this is such an important thing. It cut across so many different courses. Why don't I have it as a compulsory course to all my undergrad students? It's a big question, good question. I think we need more of you to work in this area and contribute, and maybe some of you go to academics, can contribute and start teaching courses like this, because I still feel any student graduating from a college like this, say optimization in their CV and say a few things at the interview, would be a very good product. The industry should be interested in them, because you become problem solvers, okay, in general. All right, last thing about this slide I want to say is this hierarchical optimization, which is becoming an important thing. It's the most complex optimization, one of the most complex optimization problems you can solve. Here there are multiple levels of optimization. On one level, we call upper level. In this case, I'm giving an example of a farmer government problem. The government officials or policymakers come up with tax policies of using different kind of fertilizers with different concentration of nitrogen, phosphorus in them, right? So they put, because of the environment, they say, if you want to buy this kind of fertilizer, which is very much nitrogen rich, we are going to charge you a lot of tax, because that's how we are discouraging you, right? Once those policies are made, then the farmers come in and look at the taxes, and they say, if I buy this, I need to pay so much tax to the government. Buy this, maybe little, but it's not so effective for my field. So they should find those Pareto set that we were talking about, right? So you go and find a compromise on, but they have their own optimization. They say, if I buy that, if I use that, what will be my production? What will be my profit out of it? So they have their own optimization problems to solve given the tax policies. And the government makers have to consider the farmers, because if they come up with an exorbitantly large tax, nobody is going to buy those fertilizers. They are not going to get any revenue out. So their objective could be how much revenue they are getting out of it from the taxes, and what is the environmental, have I reduced the environmental effect? Like governments oftentimes come up with policies like 5-year policies, 3-year policies, where they say, okay, we made these tax policies so that after 5 years, we're going to reduce the level of nitrogen and carbon dioxide and things like that by so many percentage. So they have a goal, they optimize their own thing, but they also have to take into account farmers. So there is one optimization at the top called upper level, one optimization, at least one optimization at the bottom, it's called lower level, but they are linked. If you change the tax policy, the farmer's optimization is going to change completely. So one optimization nested into another. So that's why it's a difficult thing to do. But we recognized this many years ago. We've been proposing some algorithms, but these are so difficult even for us and students who are working on this to visualize all of these interactions. Not many people even in academics have taken it up, but this is this is really a very a novel area and not much work has been done. So those of you who are kind of maybe at the end interested, you might look into this area. Okay. I know I'm doing terrible on time, but let me just want to make the good foundation before you do any. I would rather do one or two methods, algorithms less, but this foundation is important. Okay, so now let's talk about, so we talked about problems so far a lot and little bit of introduction to what is optimization. But now let's talk about algorithms, just overall. So we could classify the algorithms into these two classes, point-based versus population-based. Point-based is like this. We have an objective. I'm taking just single objective function here. You start with, let's say, this point. The algorithm can take you this way because it's improving. It uses certain philosophy. I'm going to show you one or two later. And you go up. In this case, we are maximizing. So you go up the hill and eventually find the maxima. Once you are at the maxima, the algorithm finds there is nothing better than me at this point around this region. So the algorithm stops. There is a termination criteria that it has. If it doesn't find anything around it, it stops and declares that as the optima. Okay. Then if you start from here, you go to another optima. If you start from here, you go to another optima. Once you've done few times with completely different set of points, and every time you get to a different place, then you see which one is the best. So in this case, if I'm maximizing, this will be the best, and you say, I made some effort, that is my best solution. So these are point-based methods. Because one point is going to another, you could do a lot of math. And there are lots of math in this optimization literature. By the way, the same optimization course can be taught in the maths department. And there are some places, IIT Kanpur, as Professor Jaideep Datta, he does that. Some other person there also teaches. I don't know here in maths department there anybody teaching or not. But they do mostly point-based, and these functions, objective functions, constraints, they are usually convex because you could do a lot of theory if you assume convexity. So they're limited, not maybe readily applicable to practice if it's a real world practical problems, but some problems you could do like linear programming. If all your objective function and constraints are linear functions of x, x1, x2, x3, there are fast methods. I wouldn't recommend any other method that you see here. You should use those specific methods. Another extension to that is called quadratic programming, where your objective function f is quadratic, maximum, quadratic order 2 of variables, and all the constraints are linear functions of this. If your problem falls into that, don't look at anywhere else. Go and use quadratic programming. In fact, MATLAB has a code called LingProg for linear programming and QuadProg for quadratic programming. You will find them in Python and any other languages on the internet as well. There are commercial softwares also available. Okay, but these population-based methods, very difficult to do math because now we are dealing with a number of points. Maybe these points you start with, and the algorithm then suggests another set of points. Maybe there are some overlapping points. So they move in populations. I will show you a simulation how it moves. Because they are dealing with a set of points, it's difficult to get stuck into a local optima like this. Because if you're stuck here, all your points are kind of converging here. It's a matter of finding a point that is better than this in terms of objective, then everything will move there. Okay, and it's a population, so you could do a lot of things. You could do something to this point, something to another point, and you can kind of be your own creator of the algorithm, right? So we'll talk about all that. So these are more global perspective. These are evolutionary optimization is one such, where we can see lots of design in nature, okay, that are like optimal. For example, the beehives being hexagonal shape, actually I give this to some semesters I give this to my students in the optimization class, an exercise, a home assignment, to show that beehives have the maximum strength per minimum area. So there is a maximization concept. You do circle, you do triangle, you do square, you do any other shape, they are not optimal. This is the optimal hexagon. So how did the bees figure it out without knowing math? Over the years of many years of experimentation. Something that didn't work, they never go back to it. Something that worked, they build up on that, they modify it, and then at some point they're still doing it actually. They're still trying to change the shape, and some places if you take a beehive, cut it, you will find somewhere it's not hexagonal. It could be octagon or something. Somehow they have fixed it. But when they experiment, it's not as strength as the hexagon, so it's going to fall. And then they die with it. So all the ideas those bees have probably have gone. Okay, so it's very ruthless in environment, but that's how according to Darwin all these things have evolved over the years. So if you follow some of these principles, because they led to very good designs, like the penguin's body is a fluid mechanics solution of low drag solution, right? So how do they figure out these things? You can find that with some experimentations and survival of the fittest kind of idea. So we try to do this in these population based methods. So these are completely different ideas, have more global perspective but less mathematical proof. So let's go a little deeper into these two methods, point based methods. You start with a particular solution, let's say some initial solution, then you update it with an update function that the algorithm already has, or if you want to design your own, you have to come up with a t function, how to transform x into a new solution y. Then you evaluate y, means compute the function and constraints, compare these two, y with x. If y is better, keep it, replace x with y. If not, forget y, keep x, and go to beginning, go to again to 2. So you move these things and always look at the termination criteria. Are you stuck? Have you got the best solution you're looking for or something? And then you stop and declare that. So this is a simple method. It doesn't take few lines of code, more than few lines of code to do this. Not much memory is needed. You just need to store two solution, x and y, but it has this local perspective because it doesn't see the entire space. It's just a local thing. It depends on t, how broad is your t function. And no parallel processing. If you have 10 processors with you, you don't know what to do with it, because you need to just evaluate two solution x and y. So they are not very much friendly with parallel processing. They are amenable for theory, because now you could do theory with just two solutions, but often they are not flexible because somebody has told you the t and they are usually complex. How to handle constraints, how to improve the objective functions in the direction of gradients and everything is all factored in there. So if you look at an optimization code, I am 100% sure, because I tried with some methods and I gave up. There are so many things going on. You need to find the original source to see how they come up with the function t. So it's not very good to change them to meet any problem requirement. On the other hand, population based optimization method starts with a population of solutions, maybe, as I said, few of them, okay? And then you also need an update thing. Now it's a different update formula where a population is updated to another population. Maybe there are some common one, as I said. Now you can compare both of them. Usually what we do is we put them together as a big set and then pick the better half of it. And that goes here into 2, and till a termination condition is set, you keep doing that. So there is no concept of gradient or any other thing. It requires memory because you need to now keep both P and Q set in your memory. But memory these days are cheap, right? So we could do that. It has more global perspective, as I mentioned before. You could do a lot of parallel processing here, right? Because if there are 10 of them here and 10 of them here, and if you have 20 processors, if you have 10 processors, that's enough because this you have already evaluated. Now the new 10 solution you have created, one you can send to one processor, independent processor, and at the same time you get all 10 of them evaluated. We've done lots of projects like that for industries okay, where they had parallel computers and we just did. This is a very simple parallelization, but there are other ways to do parallelization as well. Not much easy to do theory, because are you going to track the best or the average solution or median solution, which one? So it's a little difficult because you have number of solutions to track. But this, you can now come up with these transition formulas can be very, very simple. You could do a lot of partitioning, like I can take these two and come up with a new solution Q, a part of Q. I can take that two and do another Q, and I can have different rules for different sets, subsets. So it's very, very flexible. So I don't have just one point moving to another point, because you can't have a lot of flexibility there. But if I have lots of points and I want to find another same size of points, I could do all kinds of things, right? So it's more flexible here. I can meet a lot of requirements of the optimization problem that I have now. So these are customizable. Okay, so there are pluses and minuses I want you to understand. Okay, so with these two broad classes of algorithms, I have not given you any specific algorithm. I just said overall how these philosophies of these two kinds of algorithms. This theorem is very important. It binds all of the algorithms together. It's called no free lunch theorem. Wolpert and McCready way back in 97 came up with this proof. It basically says this: if you have two algorithms, A1 and A2, A1 could be point based, A2 can be population, or both point based, both population based. One can be even a random search method, right? If you are interested in solving all possible problems, because you want to be an entrepreneur and you want to have one algorithm in your code, and you are looking for that, you are doing this research, so you are interested in solving all possible problems. I put it in a big F. Now let's say I decide some performance measure, like how close I come to the optima. For each of these problems, I have some idea where the optimum is, or how much time does it take, or whatever, some performance measure, and I apply A1 to every problem of F, and I get a agglomerated performance measure called P1. Apply A2 to all problems of F, and when I apply them on the same computer, same number of evaluation, everything else is same, I got a performance measure P2. They have proven in that paper P1 is equal to P2. So what does that mean? No one algorithm is better than the other if you are interested in solving all possible problems. So what's the point of this course? What's the point of taking a class in optimization? Okay, so this theorem was originally proposed early 90s, around 91 or so, and it was circulating to all people who are working in optimization, because those people thought they did something wrong. It must not be true. They were I was part of it also, came to me, I saw the proof, it was all fine. We scratched our heads, we should change our field of research now, because this kind of makes this whole field dead. But then people realized we are never interested in solving all possible problems. Okay, if you are interested in solving one of those busy slides I showed you, like modeling or design or supply chain or things like that, say that's all you are going to do day in and day out. You are in a company, you are in a profession that does that. You are not interested in gearbox design, or you are not interested in a traveling salesperson problem, right? So in that case, you are never interested in the complete F. You are interested in a part of that. Then this theorem breaks down. Then the theorem also, they have parts that shows if you are interested in a subclass of problems, then there can be one algorithm better than the other. So that's called the customization, that for a given problem class, you can customize your algorithm for that problem and come up with the best possible method. Okay, so since this is, it's in 97, any student or anybody claiming big, like I've got an algorithm that is better than any other algorithm in the world, we raise our hand and say, have you heard of NFL? It's not possible, right? You have to always say what class of problems your algorithm is better. And that's fair, that's legitimate. So that basically brings up the whole issue of how do I customize an algorithm for a problem class. And we'll spend some time talking about it. So this is where we are in the context of algorithms and they're binding together. Yeah, go ahead.
So you said all possible problems, but how can you have a sort of bound
So,
of
yeah.
there are NP-hard problems and
Right,
things like
exactly. So this is not something you're going to do and figure out P1 is equal to P2, but this is more of a thought experiment that if you are interested in solving all problems, their proof says P1 is equal to P2. Okay, but they never solved all problems. Obviously, it's not possible. And that basically, once you start thinking deep into it, it basically says that what if I have minimization, one problem to minimize f, another problem to maximize f. I'll have completely different answer. Now, one algorithm may be good for minimization, but not for good for doing maximization. So you see right there, you are going to have average performance if you want to do one P1 out of it, right? So there are different problem classes out there. For one algorithm, it suits one class of problems, the landscape, the objective function, how that is, it suits it, and it does very well for that. But if you take that to another class of problem, it requires a different kind of algorithm. The same one will not do well, and that's why it averages out, and you get uniform performance over any algorithm over the entire gamut of problems. So to me, it's not any big deal. It's all intuitive, but they have done a proof. Okay, so yeah, but if I now say no, I'm interested in this narrow class. Okay, now I need to see what are the properties of this class of problems. Is it a fast deeping to the minima, or fast dipping that's slowing down, or whatever? Then I need a different kind of methods for that, which is generic method will not be able to do. That's all it basically says. But you are perfectly right. There are different kind of complexity problems in the literature, and you need different type of algorithms for each of them. Any other questions? Okay. So with this, there are different kinds of complexities the problems come up with, like you mentioned. There are problems that are non-differentiable. Your objective function cannot be differentiated, particularly if you have a discrete search space problem. Your x1 is discrete, only integers. Of course, there is no derivative that exists, right? You can have discontinuity in the search space. You can have discreteness, as I mentioned, mixed variables. You can have combinations of these. You can have very large dimensions, and it could be in variable space, constraint space, or objective space. Non-linear constraints makes a lot of difficulties to the point-based methods. Multimodalities, there can be multiple optima. Multi-objectivity means multiple objective functions. We're going to talk about more in this. Uncertainties in variables, we're going to also talk about it on the last day. Computationally expensive problems, which takes a lot of time. We have solved some problems with industries that one evaluation of one solution takes 2 days. And not to our machines, there are 500 to 600 parallel hardwares they have. I'm talking about, this is a problem from GM, General Motors. They have 500 dedicated computers running for 2 days with lots of CFD simulations. It's a combustion problem inside the cylinder, inside the engine, and then you have evaluated one. So if you need at least 100 solutions, we are talking about 200 days just to evaluate. So your optimization go into maybe more than half a year. Who has that time? So you need to do a lot of other techniques, fast techniques, which we call surrogate assisted. I'm going to just give you a brief idea at the end of that. And then MDO is something that we had a conference in the middle of December in IISc Bangalore. There's a whole complex stuff of things there, interlinking of various disciplines and things like that. Here are some sketches of how they look like. You see the discrete space can be like this. There may not be any uniformity here, but as you see this can come in different, somewhere there can be more concentration of solutions allowed, some places not, but each of them can give you a function value. Here is the minima, but how do you find it? Discontinuity may look like this, that if you come from this side, there are some function value. If you come from this side to the same solution, you have some other function value. Lots of engineering problems are like that. I will show you one example. And then the mixed nature. So if you mix up continuous, y is continuous, x is not, x is discrete. So you have, slits of functions that you see here, and somewhere there is a minima. So you need to go and find that. You see how difficult these things can be. Multimodality means this point, corresponding x vectors. they have the same objective function. If you're trying to maximize, would you find this one, or this one, or this one? They all have the same function value. Which one would you find? You don't know. So the best is to find all four, and may not be this one. This is a local maxima, so you may not be interested in that. So you find these four and then give it to the more domain expert. Okay, let them look at and see which is more feasible to produce. So there is some other objective they didn't tell you. So if you have that objective function on this scale here, another objective function, then you can look at maybe with that objective, and maybe one of them becomes now the global. Okay, let me go back. I think I did something that escaped. Okay. Then this uncertainty thing I talked to you about, robustness. You see, this is the global maxima, right? If I'm maximizing, but I give you this x value, let's say some value 10.0, but you want to, this is some dimension, you want to manufacture it. Many of you are from manufacturing side. You know every machine has some tolerances. So you set up 10 mm dia, when you do it, it may be 9.99 to 10.02. So you are here or here, and look at what happens. The function value drops suddenly. If only you can adhere to 10, you get this highest optimal value. Otherwise you are bad. So these are called isolated maxima or minima. Nobody in engineering or practice likes this kind of solutions, because today you may be achieving it, tomorrow you may not be able to achieve it, so your quality differs so a lot. You may have seen that a photocopy machine that works here, works in Delhi where it's mostly dry, may not work here or in Kolkata region because of the humidity. And if you didn't consider humidity as a factor, your machines are going to differ completely differently, and you have a lot of complaints and make bad reputations for your company, right? So these are the uncertainties that come in with any engineering solutions or designs. You need to take that into account. Rather, if you say this solution is what I like, if I declare that, even if there is some fluctuation here, you see your function value is not changing much. But this is a suboptimal, this is not as good as that, but you sacrifice that little optimality for the robustness. So we work on this, and in fact Dipanshu has worked on his thesis on this aspect. And another associated problem is called reliability. Now you say that because of this fluctuation, I'm going to not satisfy some constraints, although that specific solution will satisfy the constraints, but if you go a little bit away, your constraint gets violated. So you want to say, I know that, but I want to have a 99% reliability against constraint. So now you are going to go inside the feasible region and look for a solution. So we'll talk about some of these things later. But this is what's coming, and this is what's, the optimization literature is trying to handle. Mostly practicalities. Okay, how we are doing? Okay. So let's now move on some specific algorithms. So this was so far overall some guidelines of problems, algorithms. NFL theorem binds all of these and saying you need to customize. You can't have one algorithm for everything. Okay, this is a general formulation called NLP, nonlinear programming. If you read an optimization paper, oftentimes they talk about NLP. If any of your objective function, this is your objective function, these are your inequality constraints, as you see. Sometimes they put it with greater than equal to, sometimes they put it with less than equal to. I'm going to mention to you what I am doing here. In this case, I put greater than equal to, because all the things in my book, my first book, I did it with greater than equal to. But now more and more I realize people like the less than equal to, then slowly I moved into less than equal to. So these are some of my early slides which I kept like that. So these inequality constraints, because once you have the constraint function equal to 0, it divides the entire variable space into two parts. One is feasible, that satisfies this, and one part is infeasible, that doesn't satisfy it. Okay. Equality constraint, on the other hand, it's a line or a curve or a surface that you have in the variable space. All points have to fall on that surface, on the line. Okay, so that makes it more difficult to handle. But if the equality constraint is linear or quadratic, it's actually at your advantage, because if this constraint says x1, somehow this is very sensitive. Let me see how to do this. x1 plus x2, am I pressing it or what? Yeah, maybe this is how to do it. x1 plus x2 equal to 1, let's say. This is my constraint, okay? It's actually at my advantage, because what I could do, I can say x2 is equal to 1 minus x1. And everywhere I have x2 in my objective function, other constant, I replace with this function. So I've eliminated one variable x2, right? So equality constants, if simple, can help you eliminate some variables to reduce the search space. But if it's a very complex one, like let's say sine x1 x to the power 5 equal to something, or maybe there is a cross term here, x1 times x2, it will be difficult to replace one variable with the other, right? So then such nonlinear constraints are difficult, nonlinear equality constraints are difficult to handle. In principle, you could do with root finding methods and all that, but there are some algorithms like that, but they are difficult to handle. Anyway, most cases you are not going to consider equality constraints, because for again practical purposes, I can actually convert this into hkx less than equal to delta and hkx greater than equal to minus delta, and I can put delta which is very close to 0. Okay, so I can convert one inequality constraint into two inequality constraints by choosing a suitable delta. Oftentimes we start with a large delta, and with iterations we reduce the delta all the way down to 0, right? And there are some variable bounds sometimes where variables are specified to lie between some low value to a high value, particularly if these xi's are dimensions. Lower bound you want to set to be 0, because otherwise this is a numerical method. The method doesn't know that all x have to be positive or non-negative. It doesn't know it. So you need to put this lower bound so that you never go to the negative values. If there is a square root function or something inside, you will have difficulty with negative values. Okay, but not all methods need these bounds. Okay, all right. So our goal is to solve this problem. This is called the NLP problem, to find the x star corresponding optimal solution. Okay, so most classical point based, I call classical because that's how the optimization literature started early, I would say 60s. Before that also optimization was used, like started around World War II, because they needed to optimize their troops, how many tanks, how many fighter planes, all these should be going, and mostly they used to have linear programming problems. I talked about non-linear here. But seriously, literature in optimization started early 60s. So that's why I call them classical, but they're basically point-based methods. So you start with initial guess. This is your feasible region. Objectives, this is your variable space, x1, x2. You can imagine if you have 100 variables, a 100-dimensional space, you start with a point inside. This point can be feasible or infeasible. The algorithm suggests, now that you are here, go in this direction. These are called line searches. And the algorithm will go and find the best point along that line. So as you are going, your function value reducing. When you cross this, it's increasing again. So you stop at that point and then declare end of one iteration. There are methods to find that, I'm going to tell you soon. So this is the end of one iteration. This could be your x0, this will be your x1. Then the algorithm says, oh, now that you are here, go in this direction. How does it find? Okay, whoever has developed that algorithm has come up with a method. So I'm going to show you a couple of methods. And then you do the same thing and you find this point x2. And like that you go, I showed you those zigzag path, this is how it's done. Okay, and then you go this way, approach near the minima. Now if you started from somewhere else, maybe it takes a shortcut. Okay, maybe you start from another place, maybe it doesn't take a shortcut, it just go like this and it take long cut and finally get there. Okay, so that's why same problem with different starting points may have made the problem more simple or more complex. And there is not much really theory there, unless of course you know where the minima is roughly and you start around there, then you are already providing that kind of information. Some of the customization I talked to you about is with that. if you have some idea where in the search space your solution could be, and oftentimes as a practitioner you know that with many years of experience, you can utilize that here. Okay. So we need this directional search for these point-based methods. So you have a point, this is called a directional search. You've seen these horses, right? They put, when they are driving a car, they put this kind of mask on this, they only see front, they don't see elsewhere. They don't want to get jittered about what's happening in the road, right? So it's basically like that. You are here and you are kind of wants the algorithm to move only in this direction. So if I have two dimensions, x1 and x2, and I want to go from this point in this direction, how many variables are we talking about? Anybody wants to try? Is this still two variables? Or how many variables are there? What do you mean by variable? That means how many things I have to change to be on the line? Only one variable. What is that variable? Is the distance from here. If you say this is 1, I am here. If you say this is 2, you will be there. This is 2, right? 1.5, you will be somewhere in between. So if you just tell me one number, because I know the direction, I know the initial point. If you give me one number, I can tell you exactly where you are on that line. So it's true for two variables, it's true for also 100 variables. If I have 100 variable space, I have an initial point and I move along a line, you just have to tell me one number. How much do I move? So although it's a 100 dimensional problem I'm solving, directional search is always one dimensional. So now we're going to talk about a single dimensional search, which is the single variable search. All I need is a variable A, is the distance along that. A times the direction, this is the vector, I add to the current point and I get the new point. So I have to basically decide what A shall I put so that I get to the optima. What A shall I have here? So this is my A. I need to find that A so that I fall on the minima. So it's a single variable search. I can experiment with A. So there are two ways to find the A. Okay, first is called the rough bounding. So first I am going to do what? I am going to bound my minima, saying, oh, minima lies between this small value to this large value. Minima is bracketing, I bracketed the minima. That's called the bounding phase method. I'm going to show you one algorithm for that. Once you have bounded, bracketed the minima, now I'll do a very thorough search in between. I'm not going to go outside this anymore and pinpoint where the minima is. That's called an accurate bounded search. Or I'm going to show you one method, which is the golden section. This one is called bounding phase. So let's start with bounding phase. Both of these algorithms assume one thing, that there is a single minima along that line. Along that line, there doesn't exist a minima here, another minima here, another minima. No, there's only one minima, and that is that one. That's the assumption. That doesn't mean you cannot apply these methods to multimodal problems where there are multiple minima. You can apply, but you never guarantee anything. Okay, but let's go ahead and even look at that. So let's say here's my direction. So I have one variable x, this is the A, but I can call it x. The algorithm starts like this. You need a x0, you need a starting point along that line. So for this problem, my starting point A is always 0, right? Because I want to start from where my initial point is. So this could be 0, and this you can supply, let's say 0.1 or 0.2 or 0.5, whatever. You supply some value. There are some implications with that, but okay. Now these two are given. What you do now, you go x0 by delta along the direction that you want to go, and go another delta. So these 2 points you create, x1 and x2, evaluate these three values. If it's like this, that x0 has a worse value, I'm minimizing here by default, okay? x0 has a bigger value than x1, x0 has a bigger value than x1 has a bigger value than x2, which means in the direction of my direction, function values are dropping. Then I want to go in this direction. I really want to go in this direction to find the minima. On the other hand, if I had this situation, so this is my x0, x1 and x2, what will you do? Which direction you are going to go? The other direction, because looks like that's where the minima is. So I'm going to simply change the direction of delta as minus delta. I'm going to go in the other direction. Okay. What if there are two more situations? What if I have something like this? So this is again x0, x1, x2. What shall I do? Which way shall I go? Right, I already stopped because my goal here was to bracket the minima, and I have bracketed. You see, minima, either minima is like this or the minima is like this. So, but minima is in between x0 and x2 if you assume there is single minima, right. So, I do not need to apply this bounding phase. I was so lucky to give a x0 and a delta that my minima is already bracketed by x0 and x2. So, my bracketing here is x0 comma x2, not x0 comma x1 or x1 comma x2, because any of these two ranges minima can lie. But I have already bracketed, I can stop the algorithm and declare. There is a third situation which can be like this. Then which direction shall I go? Now it's difficult to say which direction I'm going to go. So basically you change your x0 or change your delta. Just make it bigger so that maybe this one and another, maybe now I find something. So just increase delta or change the x0 location because it's not a good starting point. Alright, so I can, then I have a start, okay. Some cases I'm stopping already. Now you put k equal to 1 and use this formula to get x1. So you see k equal to 1 means this is x0, which is this one, plus 2 to the 0, which is 1 times delta. So basically you get x0 and x1 and you compare x1 with x1, x1 with x0. If x1 is better than x1, if I am minimizing, if x1 is smaller than x1, then continue, then you move there, okay. And then moving there means you are going to increase your k to 2. When k equal to 2, you get x2 equal to x1, I am just writing this for k equal to 2, plus 2 to the 1 times delta. So from x1 I am going to go 2 times delta. So for x1 I am going to go 2 delta. So here there is a little mistake, I am going from x2 but it should have been from x1. But let us say this is my x1 and I move 2 times delta and I come here. Let me see if this is, yeah. So I should have gone x1 to delta. So let's say, okay, let's put it the correct way. So this is my x2 now. My original x2 was to get this direction set. Now I come here and this is my x2. So now I compare x2 with x1 and I say x2 is still better. Then what I am going to do, I will compute x3. So what will be x3 now? K is now 3. x3 is going to be x2 plus 2 to the 2 times delta. So now from x2 I am going to go 4 delta. So from here I am going to go 4 delta. 4 delta is this much, so I am going to come here. So this will be my x3 and I still see x3 is better than x2. So next is going to be x4, which will be x3 plus 2 to the 3 delta, which is I am going to go 8 delta, I am going to be here. So this is my x4. I still see this is better than x3, but you see my optima is here, I have already crossed it, but the algorithm does not know, because algorithm does not know here there is a minima, it is just finding few discrete points. So it just come here, so algorithm will move on. So x5 will be x4 plus 2 to the 4 delta, which is 16 times delta. So I will come here, this will be my x5. Now I see that x5 is worse than x4. I stop. I don't have to move any further. I have already bracketed. What is the bracketing? Is it x4 to x5 or what? So the bracketing is always xk minus 2. So k here is 5. So it will be x3 to x5. So x3 to x5. So this is my bracketing. I am basically saying between this x3 and x5 my optima lies. You don't have to consider less than x3, you don't also consider more than x5. Does that make sense? For single optima, this always works. Okay, now if I have chosen small delta, I probably would have bounded like this, okay? Or if I have chosen my x0 somewhere close, maybe I would have an even tighter bound because I haven't gone 2 to the 4, 2 to the 3 or something. So you see, exponentially you are approaching the minima, but if your delta is large, you may have a larger bound. It's a matter of luck. Where you start, what's your delta, depends on what you at the end get. But doesn't matter. All goal is to bound the minima. Minima should be in between the lower and upper bound. And this one does that job. Okay, understood? Because you are going to do a home assignment with this. Okay. Once you've done that, now comes pinpointing where the minima is. It's called the golden section search. So what we do there is, this lower bound, that x3 that you had there, and the upper bound which was x5 here, whatever was the value, you are going to map x3 to 0 and x5 to 1, so that my golden section search is always between 0 and 1, because you have now two bounds, so you can map 1 to 0, lower bound, upper bound to 1. It's a single variable, right? Now the golden section, all of you know about the golden number. Maybe those of you in civil engineering have studied it. It's a number associated with pleasing your eye. Okay, many buildings are made with this proportion of 0.618. Your fingers, if you go from this end to the second one, and the whole length, if you say, if this is 61.8%, you can measure going home, your finger will look the most beautiful way. Okay, they have done that on many beautiful women about their face, like until the eyebrow to the chin and eyebrow to the head over here. If it's 61.8%, your face already looks beautiful. Okay, so the ladies here can try that going at home. So this number is used in many different fields, actually, started with the civil engineering, structural optimization kind of areas. But we see that here too. What this number does, you'll see, it does a wonder. The idea here is that you have 0 to 1, you go 61.8% on either end. So you come 61.8% from 0 and 61.8% from 1, which means 38.2% from this end. Okay, you got 2 points. What you do now, you evaluate, so this needs to be mapped back to A, because A is between x3 and x5. Okay, and you can always kind of map it. So your A mapping is going to be, if I think it properly, it's going to be, so when you have x3, it will be 0. So how will this be? So this will be 1 minus 0 divided by x5 minus, if I am thinking it properly, x3. Over here it will be just x3, I think. Let me see, x5. So am I doing it right? x3, so this will be the x value here, so I need, so sorry, it will be alpha minus x3. Yeah, alpha is the value here. So so let's say, so this is if you know the value here, but if I give you the value here, what will that be? So when it's 0, so A is going to be 0 when x3 is equal to that x is equal to x3. It's going to be 1, then this is equal to x5. So how will I map it? So how will A be as a function of x? So x minus x3 I need, okay, because then it's 0, and then when x is x5 I need to, simple, this formula. Okay, so if you use that, put x equal to x3, put x equal to x3 will be here 0, and put x equal to x5 you will be here as 1. So that's the mapping. So now you can actually from this calculate what should be x. So these are always A axis is here. So give a value 0.382 here and you find the corresponding x, and that x you are going to use to compute your objective function. Okay, so you know that. So let's say at these 2 points my objective function is such that this value is bigger than this value. Now let me tell you one thing. I am assuming that there is a single minima from 0 to 1, and I find this fact that this point has a bigger value than this. Now, which of these three places, region 1, region 2 and region 3, which of these three places I do not have my minima, assuming there is a single minima? Can you reason it out? R1, because either the optimum is here or the optimum can be here if my function goes like this with a small slope and goes up, right? But optima can never be in R1. So I can actually eliminate this part for my next iteration. So I have from 0 to 1, I have reduced it by 61.8%. You see how powerful that is? Just with 2 evaluations. Okay, so let's say in this case I am back with this region. Now I am going to use the same principle, 61.8% from either end. So this is already 61.8, 0.618. 61.8% of 0.618 is 0.382. So I go 0.382 from here and I will be here, and 0.382 from here and I will be here. What's the magic here of this number? And that happens only for this golden number, is that one of these is going to match with one of the others you have already evaluated. So you see this one matches with that. So this point I don't have to evaluate the function, I've already here evaluated it before. There is only one new function I have to evaluate. You try with any other number like 0.619 or any other, it's not going to happen. It's going to be a slightly different point. That's the beauty of this number. Okay, so you have to remember that number. All right, so now that I've got these two, I evaluate the functions and I find this is bigger than that. So which part I'm going to eliminate now? This is bigger than this. So which of these three part of R1, R2, R3 I'm going to eliminate? R3, right? So R3 I eliminate. So now I am back with this. I do again 61.8% of this range. From either end, one of them is going to match, the other is going to come here. And now I evaluate, you will see now that it will be slightly higher and this one I will eliminate. So what will happen is this process will continue, but the minima will never get eliminated. And you are reducing your range by 38.2% every iteration with one extra function evaluations. This is known to be the best possible algorithm. With a single processor computer, every iteration with one function evaluation, you eliminate 38.2% of the previous region. Make sense? So this is the most efficient algorithm. Don't look for any other algorithm. So this is going to pinpoint, but in the assignment I asked you to do only 3 iterations. With 3 iterations, you are not going to pinpoint it. How you are going to pinpoint? When the two values, this lower bound and upper bound, has a 3 decimal places of accuracy. So maybe this number is 1.2385, the other one is 1.2382. Within 3 decimal places, you say stop. I'm not going to go any further because it's only going to split now the 4th, 5th decimal places, so no point for me to continue. Okay, and pretty quickly, if you code it pretty quickly, it happens. All right, so that's the way I go every direction. I start with my current point, find which way to go, and then I bracket the minima, and then apply golden section. Okay. Some algorithms use gradient. This is a numerical way you gradient. This is called central difference method. You perturb x with delta x and reduce by some delta x and take the difference with 2 times delta x. There is a way to choose delta x, but all these you will have in your material. I need to speed up a bit here. Yeah, maybe I'll give you a break at 11. Next one is multivariable optimization, where this was a single variable, as you've seen, right? And all these methods, bounding phase, golden section, works only for single variable. Multivariable, now you have a vector. There are more than one variable space. There are lots of different methods. These are direct search methods, do not use gradient, and the gradient based methods that use gradients. Okay, I'll show you 1 or 2 of every type. So simplex search is coded in many different methods. MATLAB has a method called fmin search. Okay, I'll show you soon. Fmin search that uses this Nelder-Mead simplex search method. What it does in 2 variables, it starts with a triangle, 3 points, and then it finds out which one is the worst. Here this is the worst. So what you do is, other values you find the centroid and reflect this point the same distance the other side. You get XR, reflected point, evaluate this function, at this point compute f, compare with these two and these three basically. If this is better than the best of the three, that means you landed up in a good place. What you do, take a bit of adventure and go 50% of these distance, okay, take 50% of it, add to this and get your new point. Forget that because that was the worst, and now this is your new simplex, and apply the same process. If this point is worse than the worst one, you come back to the middle here, middle of this, and this becomes your new simplex. If this is better than the second best but worse than the best, you come here in the middle and this becomes your simplex. These things you can change, okay, but this is what they did way back in early 60s, I think. And then what happens is this triangle starts and then it flip-flops, changes its shapes and approaches this area where the minima is. Okay, by the time maybe you come here, and then every time you try to reflect, like reflect is going to be worse. So you come back and put in the middle and your triangle becomes like that. And you see your triangle reduces in size because outside is bad, only inside is good. So you try to reduce, eventually this triangle is so small, all the 3 points are within 3 decimal places or so, then you say stop. So that's how it's happened. You start with the big triangle, it flip-flops, it goes near the minima is, and then it shrinks and becomes small. Okay, it's nice to see it on a animation how that works. Then there is gradient based methods but that was without gradient, right? This one, you start with a point, not 3 points, but with a point, and compute the gradient direction. You know the gradient is the direction in which the function values increases the most, right? If you go in the negative direction, your function value will reduce the most. So, and because you are minimizing, so that makes sense to go along the negative of the gradient. You go along that direction. Now it's a directional search, like bounding phase and then golden section, you're going to pinpoint it. Okay, that's the end of one iteration. Then you find the gradient again and go in the negative of the gradient and repeat best point, and within few iterations you can come close to the minimum. Okay, but this requires gradient of the objective function. There is another concept called Newton's method, which uses second order derivative, and there is a combined method called Marquardt search method, where initially it uses gradient steepest descent method, later on it follows up with a Newton's method, because when you are very close to the minima, the gradient values are so small, the directions get wrong information. If you now look at the second order information, like right here, if you use second order information, you get more information actually. So that's why starting with steepest descent, ending up with Newton gives you the Marquardt is a much better search, and many commercial codes are coded with this. The last one I'm going to talk before break is the quasi-Newton method, where Newton's method uses second order derivative, and second order derivative needs lots of function evaluations if you want to compute it numerically. So there are pseudo Newton's method. What it does is it starts with assuming the Hessian matrix, which is a second order matrix, as an identity, and it transforms the identity matrix into Hessian inverse. Actually it's the Hessian inverse, which actually gives you near the minima. So these transformations are very complex, very difficult to understand how they came up with those things, but it works. They are always symmetric matrices and positive definite matrices. So there are this DFP series and then BFGS series. These are also popularly coded in many algorithms. For quadratic problems, all these methods have a proof that you are going to achieve the minimum with, I think, just few iterations. I think it talks about the number exactly depends on which one of these. That's the gradient based is Hessian requires 2n square plus 1, where n is the number of variables. If you have 10 variables, you are talking about 201 function evaluations already. And remember that problem I showed you, one evaluation takes 2 days. One Hessian matrix takes 201 in that case.